Today we're looking at lesson 6.3 for geometry, which is tests for parallelograms. And this is basically giving the conditions in a few theorems to make a quadrilateral be considered a parallelogram. So we're going to use these theorems in the examples. So the first example, we're supposed to determine whether the quadrilateral is a parallelogram. Notice that the first quadrilateral has two sides opposite to each other that are equal, two pairs. So if you look at the first theorem, 6.9, that would say that this would be considered a parallelogram, and your justification would be theorem 6.9. Now the second parallelogram has one pair of opposite sides congruent, but then one pair of opposite angles congruent. So if we look at the theorems, we need both pairs of opposite angles or both pairs of opposite sides to be congruent. So this doesn't give us enough information, so we would say no, because none of the tests for the parallelograms would be fulfilled here. Next one, this was at the beginning of the lesson. It says Lexi and Rosalinda cut strips of bulletin board paper at an angle to form the hallway display shown right here. Their friends asked them how they cut the strips so that their sides were parallel without using a protractor. So Rosalinda explained that since the left and right sides of the wallpaper or the paper were parallel, she only needed to make sure that the sides were cut to the same length to guarantee that a strip would form a parallelogram. So we're supposed to explain why the cuts made by Lexi and Rosalinda are parallel. So if we look here and we name this, let's say, to be A, B, C, D, we know that she's making sure that the sides were cut to be the same length. So that makes AB or AD, equal to, or no, sorry, AC equal to BD, these. And we know that this is telling us that the sides of the bulletin board paper are parallel already, AC and BD. Then we can say by theorem 6.12, if one pair of opposite sides is congruent and parallel, then the quadrilateral is a parallelogram. That would tell us then that the cuts that she's making every time are going to be parallel because it's a parallelogram. So we know that A, C, and BD are congruent and parallel. Then we need to, for this next example, find x and y so that each quadrilateral is a parallelogram. So we need two sides, two opposite angles congruent to each other. So we're just going to put 7x equal to 56 to find x, since they're opposite angles. So x would be 8. And then to find y, do the same thing. 5y minus 26 equals 4y plus 4. And solve for y. So y minus 26 equals 4. So y would be 30. And x would be 8. Same thing here, except we have opposite sides. So we're going to do opposite sides equal to make this a parallelogram, and solve for x. So x is 3, and then y would be the same thing. 4y minus 9 equals 2y plus 5. Solve for y. Y equals 7. The last couple examples here, we have 3 more. You're going to determine whether the quadrilateral is a parallelogram, but you're going to justify yourself with the formula that they give you, so we have to use the formula they give you to explain. So this first one, they give us coordinates, and I would plot these on a coordinate plane just to get a visual, but we're not going to go by what it looks like. We're going to have to use the distance formula to prove that this is a parallelogram. So A is 3, 3, B 8, 2, C 6, negative 1, and D 1, 0. So by first look, it does look like it's a parallelogram if we connect. But to prove that it's a parallelogram and using the distance formula, since we have to use that formula particularly, I would find the distances of AB and DC to make sure those are congruent, and then the distances of BC and AD to make sure those are congruent, and just use the distance formula. So AB and DC, 3, 3, 8, 2, and DC 1, 0, 6, negative 1. We're going to use a distance formula for both of these to say that they're congruent. So to review, that is subtracting the x's, squaring them, subtracting the y's, squaring them, then adding that together and taking the square root. So negative 5 squared plus 1 squared, 25 plus 1, or 26. So the square root of 26, and then we're going to do the same thing with 1, 0, and 6, negative 1. So 1 minus 6 squared plus 0 minus negative 1 squared, negative 5 squared plus 1 squared gives us 25 plus 1, which is again square root of 26. So we've proven that AB and DC are congruent. Then we're going to prove that AD and BC are congruent. So 3, 3, 1, 0. And BC 8, 2, 6, negative 1. So using the distance formula, 3 minus 1 squared plus 3 minus 0 squared. We get negative 2 squared plus 3 squared, or 4 plus 9, so the square root of 13. And then to do the other set, 8 minus 6 squared plus 2 minus negative 1 squared gives me 2 squared plus 3 squared, or 4 plus 9, so the square root of 13. So we've proven that two opposite sides are congruent using the distance formula, so we can say yes, this is a parallelogram. Now the next set, it wants us to use the midpoint formula to determine whether this is a parallelogram. So if we look at the theorems in the beginning, one of them tells us about if diagonals bisect each other, then the quadrilateral is a parallelogram, 6.11. So if we do the diagonals and do the midpoints of those, if they have the same midpoints, that means that they're going to bisect each other, and they're bisecting at the same point, the midpoint of both. So if we do that, we would need to find the midpoints now of AB and DC, or in this case, we have a different set of letters. We're going to need to find the midpoints of these, so I would graph these first to get a better picture of which lines to get a midpoint for. And again, it looks like it may be a parallelogram, but we have to prove. So we need the midpoints of FH and GJ. So FH, negative 2, 4, and 4, negative 2. And then the midpoints of GJ, 4, 2, and negative 2, negative 1. So the midpoint here, we need to add the x's, divide by 2, comma, add the y's, divide by 2, and we get 2 over 2 and 2 over 2, which is 1, 1. Let's see if it's the same. Two over 2 and 1 over 2, so not the same. So this would not be a parallelogram because the diagonals are not intersecting at the same midpoint. The last example, we're supposed to write a coordinate proof of this statement. So it tells us if a quadrilateral is a parallelogram, then opposite sides are congruent. So for this one, we're basically going to be assigning letters to points like we did when we were doing the coordinate proof. So we have, let's say we drew our parallelogram, we would always want to start at the origin, and then we could have that be A, and then we have on the x-axis, remember we use A, so we're going to do A, comma, 0, and then we usually do for the y-axis B, so B, we could do this since it's partially down A as BC, and then we know that it has to be for the last letter B plus A, also comma C, so we can do this one as B, D, C, and label our parallelogram. And basically what we're going to do here is we're going to prove that opposite sides are congruent by using the distance formula. But we're going to be using the letters that we assigned instead of numbers. So if we have, let's say, AB, the distance formula, 0, 0, A0, it's 0 minus A plus 0 minus 0. That gives us negative A squared plus 0 squared, or just A squared, and then we take the square root, so it's really just A. That would be the distance here. And then we do the same thing for DC, so that's BC and B plus A comma C. So B minus B plus A squared plus C minus C squared. These cancel out, so you get A squared, and C minus C is 0. So again, you have A squared plus 0, square root of that is A. So we know that this DC is also A. Now we're going to do the same thing for AD and CB. So AD, 0, 0, BC are 2 points. Distance formula. Oops. So B squared plus C squared, square root of that. Let's see if we get the same thing. For BC. So A minus A will cancel out. You get B squared plus negative C squared, which makes it positive. So we get B squared plus C squared. So we've just proven, using the coordinate proof, that this is a parallelogram. And that concludes lesson 6.3 for tests for parallelograms.